Welcome to the talk. I'm Yuxiang Peng from the University of Maryland. Today I'm talking about the algebraic reasoning of quantum programs via non-idempotent Kleene algebra. This is a joint work with Mingsheng Yin and Xiaodi Wu. We motivate this talk with a classical compiler rule called loop unrolling. Here we have two programs, unrolling 1 and unrolling 2. They only differ at the loop body. You can see that the right one has a loop body unrolled once with an if statement. We say that these two classical programs are equivalent in the sense that they have the same semantics. Now we switch the context to quantum programs. Here you can see that the loop guard now is replaced by a quantum measurement. Quantum programs have many marvelous features. For example, when you apply a measurement, the state will change, and the quantum programs have intrinsic non-deterministic nature. As an example of quantum measurement, if you measure the superposition of a black cat and a white cat, with 50% probability, the result will be a black cat, and with 50% probability, the result will be a white cat. It is very hard for people even familiar with quantum programs to determine whether these two programs are equivalent. And actually, they are not equivalent. For example, if we use a coin toss measurement here for the loop guard and the if statement here, you can see that they are actually not equivalent. For unrolling 1 program, the while loop will quit instantly after the first success of the measurement. And for unrolling 2, you can have the subprogram P executed after the first success of the measurement. However, if the measurement M here is a projective measurement, then these two programs are equivalent. Our goal is to find a way to investigate whether the two quantum programs are equivalent. For classical program equivalence, there's a well-studied approach called Kleene algebra with tests, abbreviated as CAT. CAT basically encodes programs into regular expressions and uses a set of axioms to derive an equation and shows that the equivalence of the program. The encoding is also suitable for quantum programs, since the quantum program have the similar program constructs compared with the classical ones. For example, we can use a Kleene star operation to encode the while loop in unrolling 1 example. Now our problem turns out to be, what are the axioms for quantum programs? And are the set of axioms a sound and complete one? Our solution is through the non-idempotent Kleene algebra. You can see the axioms of this algebra listed on the right. We can use a series of algebraic derivations to show the equation of the two encoded expression for the two programs, with the premises encoding the projective measurement. The main theorem of this work is to show the soundness of this approach. Basically, it is saying that if you can derive the Hoare formula under the axioms of NKA, where the Hoare formula encodes the quantum program's equivalence, then actually you will get the equivalence of the denotational semantics of the two quantum programs. Here, we give an overview of this talk and all the technical details. We start with encoding quantum while programs via NKA. As you can see, all these concepts are previously studied and like well known in some small fields. We basically provide the link between these concepts, which is called quantum path model. The quantum path model is a sound and complete model for the axioms of NKA. And the denotational semantics of the quantum while programs are embedded in quantum path model, basically saying that what you derive in the quantum path model can be mapped back for the quantum while programs. With this model, we can derive the main theorem and exploit the main theorem to give algebraic proofs for compiler rules verification and the normal form theorem. We also equip the NKA with tests to characterize quantum predicates and quantum measurements. We can use NKA with tests to give an algebraic proof for the propositional fragment of quantum Hoare logic. Now we dive into the details of all these concepts. We start with the Non-Idempotent Kleene Algebra, abbreviated as NKA. It basically removes the idempotent law P plus B equals to P, which is marked red, but it's small. They are in the right figure from the Kleene algebra. With the removal of the idempotency rule, the original partial order is no longer exist. So we replace the partial order by any partial order, while the addition and the multiplication are monotone. In 2004, Ishik and Kuish have shown that many rules that is in Kleene algebra still holds in NKA. For example, we have a selection of very important rules that is frequently used for compiler verification, listed here in the bottom of the page. We also have many known facts about NKA existing in the literature. For example, in 2009, Bloom and Ishik has shown that a weighted version of a formal language called rational power series over extended natural numbers is a sound and complete model for NKA. 60 years ago, Schusenberg proved that there's a link between weighted automata and rational power series, basically saying that they are equivalent concepts. This link between weighted automata and rational power series gives the complexity for problems related to NKA. For example, deciding NKA equation is a piece-place complete problem, and deciding NKA inequality is undecidable due to an earlier work of Eilenberg on the weighted automata. We then show how to encode quantum while programs, as formally defined here. We basically encode them into regular expressions, and you can see that many elementary operations, like qubit reset, applying unitary transformations and measurements, are abstracted as symbols. So their information is lost. When we actually need them in the algebraic derivation, we need to import them as premises when necessary. A key issue here is that the Kleene star operation, which ideally will be defined like in this equation, is actually partially defined for quantum channels. For example, if you apply the Kleene star on the identity channel, you will result in an infinite sum which is divergent. We want to avoid the use of partial functions for the elegance of our algebraic approach, because if you have partial functions, you will have to check the domain of every rule you apply, and that is very cumbersome. To deal with it, we propose quantum path model to include the Kleene star operation. It is basically named because quantum processes take sum of all paths. The key observation here is that we need to distinguish different infinity for the infinite sums. For example, if we apply the computational basis measurement, which resulting in 0, on the infinite sum of state 0 and on the infinite sum of state 1, they will result in different behaviors, so that we need to distinguish the infinite sum of 0 and the infinite sum of 1. Our quantum path model is basically a generalization of quantum states and quantum channels. Basically, we generalize quantum states to equivalent classes of quantum state multisets, and generalize quantum channels to linear and monotone transformations of these PO infinity states. Interestingly, the quantum path model has subsumed the quantum states and quantum channels, meaning that if we have derived equations in quantum path model, we directly get equations for quantum states and quantum channels. We now interpret the expressions into quantum path model by quantum interpretation. The quantum interpretation takes symbols into quantum channels that is lifted into quantum path model. We prove that with a proper interpretation, the denotational semantics of the program is recovered from the encoding of the program. And basically, we have a relation between the algebraic expressions and the program semantics. We have proved a sound and complete result, saying that with respect to the quantum interpretation, the axioms of NK are sound and complete. That is to say, for any expression E and F, they are equivalent under the axioms of NKA if and only if for any quantum interpretation, the result is the same. This basically implies that NKA captures all the equations if any symbol can be interpreted as any quantum channel. The soundness side of this theorem leads to the main theorem. And we can exploit the main theorem to provide proofs and verifications for quantum compatible rules. We will use the loop unrolling example, whose encoding is listed on the left-hand side here. We have a short animation to show how this derivation is proceeding. We make use of the derivable rules that coexist in Ka and Nka, which includes denesting, fixed point, and unrolling rules. We also make use of the encoded premises about the projective measurements as m1 times m1 equals to m1, and m1 times m0 equals to 0. With a series of rule application and algebraic derivations, we can finally get the two expressions encoding the two programs are equivalent under the axioms of Nka and the premises. Applying the main theorem, we have formally verified that the denotational semantics of these two programs are equivalent. We have more examples in our paper, and we refer you to all these interesting examples. We also give an algebraic proof of the quantum Bohm-Jacopini theorem, a normal form theorem for quantum programs. It basically says that for any quantum program, there is a equivalent quantum program with only one while loop. This theorem is observed by Nengkun Yu in 2019, and we give the first algebraic proof to it. The proof idea is simple. We basically redesign the control flows for the program constructs inductively, and then prove their equivalences via Nka. We can also further characterize quantum programs by introducing tests to Nka. Like what has been done for Kleene algebra with tests, they have encoded classical tests with Boolean algebra. Classical tests actually serve two functionalities. The first is the property test, and the second is the branch guard. However, for quantum programs, these two roles are fulfilled by two different concepts. As you can see in the table, quantum predicates serves as a property test, and quantum measurements serve as the branch guard. To deal with them, we basically introduce two algebra objects into the Nka algebra. We use an effect algebra embedded in Nka to represent quantum predicates. The effect algebra has 5 axioms, and they are widely used to describe the events that can be observed for quantum mechanics. We introduce partitions, which is a set of elements that satisfy several properties related to quantum predicates to characterize quantum measurements. The relations between all these concepts are pictured in this figure. With quantum predicates defined, we can basically encode quantum Hoare triples by inequalities in NKT. Here, the negation is defined in effect algebra. NKT naturally subsumes the propositional fragment of quantum Hoare logic, which is listed on the left-hand side here. Their encodings are the formula E on the right-hand side, and each of these formula can be derived algebraically in several lines of proofs. It is easy to see that the algebraic reasoning of this Hoare logic is much easier than the complicated matrix analysis of quantum channels for the Hoare logic. We also give some future directions along the line of Nka and Nkt. The first part is about applications. The first question is, can we extend Nkat to quantum netcat in the application of quantum software-defined networks, like the success of netcat? Can we further characterize the quantum measurements in the algebraic way to better understand the difference between classical measurement, projective measurement, and general quantum measurement? The second part is about automation of Nka. As we have noticed, there is a close relation between Nka and weighted automata over extended natural numbers. So maybe we can use bisimulation and co-algebraic techniques to accelerate the decision procedures related to Nka. We can also imagine a formal system in Coq that builds the relations for Nka. and we can get mechanized proof the equations for NKA. And that is all. I'm happy to take any questions.
This is maybe a basic question. Is there an intuitive explanation of why removing the idempotency law is the appropriate thing to do when reasoning about quantum programs?
Well, quantum programs are it's very similar to probabilistic programs, where the branching are actually not idempotent in nature, since you have some probability of executing one path and some probability executing another path. So they should be algebraically treated as an addition in the sense of the probabilities. So basically, you don't have the identity rule for quantum programs.
So there are also like classical probabilistic programming that also like kind of share the similar property like non-idempotent. So can your framework also like capture the thing that is unique to quantum, like quantum interference or something?
Yeah, that is a good question. So about quantum inference, those information needed to verify that kind of facts are actually abstracted away in our way of dealing with this. We only deal with the structural information and basically the control flow of the programs. But as you can see, for probabilistic programs, if you have similar treatments that abstract away the detailed, explicit description of probabilities, you will result in the same algebra as we did here.
All right. I have a question, actually. Let me just check my notes really quick. So with this sort of algebra, is there a notion of over-approximation? Or does it precisely model the semantics of the quantum program?
Yeah, I think currently we are all, no approximation is involved in this kind of way to dealing with quantum programs. But if you want to basically add more approximation like tools in Netcat, it's still possible to do that, but it's not the main focus of this work. But actually, it should be like a very promising future work.
Wonderful. Okay. Thank you again for the great talk.